Hello and welcome to a short version episode of Sterling Seismic and Reservoir Services video series on reservoir analysis geophysics. This episode is titled Imaging Reservoir Fractures with DAS Seismic Data Using Diffraction Pre-Stack Depth Migration. I'm your host, Brian Fuller, VP of Reservoir Geoscience at Sterling Seismic. A longer version of this episode that contains more details is also on our website. This presentation discusses the case in which there's a surface seismic source and fractures near and even crossing a DAS fiber. Of particular interest is where the DAS fiber is in the horizontal part of a well. According to recently published modeling results, even small fractures on the order of millimeters across should generate diffractions. In the following slides, I'll show that diffractions do in fact occur in real DAS data. In a minute, I'll show fracture images in a time-lapse data set. Here's a sketch of the field setup of that data set. The well and the DAS cable are vertical to a depth of about 9,000 feet and then turned horizontal for about 4,500 feet. We have 96 vibroseismic surface shots spaced at about 150 feet at the surface, and the sources extend about 5,000 feet off either end of the horizontal part of the well. The baseline survey was recorded before the frac job, and the second survey was recorded 4.5 months later after flowback and initial production. The next slide shows the P-wave fracture image prior to the frac job. This image is in depth, with the vertical axis being depth, and the horizontal axis is data channel number along the DAS cable. Each channel is 13.2 feet apart. The DAS cable location is shown here as these red dots going horizontally across roughly the middle of the image. The blue areas in the background indicate a lack of diffraction energy, and the green and the red show diffraction images, with red being the highest amplitude and the green being between the blue and the red amplitudes. Again, the data was recorded before this well was fracked. The diffractors that we see here in the image can be either naturally occurring fractures or fractures that were created by fracking nearby wells, which we know crossed the wellbore in this well because we saw them cross the well during microseismic operations. Now we'll look at the diffraction image 4+ months after fracking, which is followed by flowback and production. The amplitudes are comparable between the images because this data set was processed for time-lapse analysis. Here's the time-lapse image. We can see that the completion and production process has resulted in more fractures. I'll flip back and forth a couple of times so you can see them. How would a frac engineer use knowledge of fracture locations to plan pump schedules, perf cluster locations, or plug locations? The sketch shown here is a hypothetical toe-up geometry with fractures that we could image with the technology shown above. Right away we can see that 25% of the well at the heel, or the left end, has a lot fewer fractures than the remaining 75% of the well. It's likely that an engineer would pump a stage at the heel into the well differently than they would for the stage between, for example, the two yellow plugs, where there are several fractures within a perf cluster range. For example, in the fractured zone, they might pump diverter to minimize flow into the open fractures. We can also see that fracture density is greater below the well than above. What does that say about the rock properties differences above and below the well that will affect the frac parameters? All of this discussion above goes for the initial frac job as well as for a refrac of the same well. We can also use this and some other closely related technology to map pressure drawdown zone into existing wells. If we're going to frac a child well next to a producing well, it's important to know about the pressure sinks in the existing well. We know from microseismic and engineering studies that low pressure zones attract fractures from adjacent wells when the new well is being fracked. Frac dollars that are spent fracturing zones that have already been produced are largely wasted dollars. Additionally, probably even worse, the reduced pore pressure zones reduce the fracture penetration on the other side of the new well, further reducing the value of the frac effort. So knowing where pressure sinks are is useful in frac design work. If you have questions about this or any other technology that's discussed on our Tech Talks webpage, please give us a call or send an email to one of the addresses shown here. Thank you for your time, and thank you for watching.